So the motivation for this study is the moderate correlation between static and EEG-based connectomes. So although we know there is this robust but moderate correlation, the relationship between time-resolved connectomes and slow and fast timescales is much less well understood. These results pose some questions. For example, what common spatial ingredients are used to describe connectomes at slow and fast timescales? And do connectomes at slow and fast timescales display similar temporal dynamics? So to answer these questions, we analyzed the co-activation patterns in concurrent fMRI and EEG across 26 subjects. So we derived a set of 126 state blueprints, which together comprise all possible combinations of the 7 Yau networks. So these are the blueprints 1 to 126. First 7 blueprints correspond exactly to the 7 Yau networks. And then we have all possible combinations of the 2 networks, all possible 2 network combinations, and they're all the way to all possible 6 network combinations. So if we correlate these blueprints to the frame-wise co-activation patterns at each time scale from infraslow fMRI to EEG gamma, we can assign one of the blueprints to each time frame as the best fitting blueprint. And this generates a different sequence of best fitting blueprints at each of the 6 time scales. So this is the sequence of best fitting blueprints at the infraslow fMRI timescale. And these are the best fitting blueprints for the 5 EEG bandpass timescales from delta to gamma. And right away we can see there's a change in the speed of expression of the templates at each of the different time scales. So this is over about 2.5 seconds. So to illustrate what's occurring here, we first display the sequence of best fitting templates, and that includes all 126 at each of the 6 time scales. And below that, we show the spatial correlation of the first 7 blueprints with colored boxes indicating when that particular blueprint is the best fitting blueprint out of the 126. So the color coding here corresponds to the Yau networks, and the color coding here and here, etc., correspond to the 126 blueprints. So we can see right away the change in the speed at which these templates are expressed is reflected in the rate of change of the spatial correlation. So fMRI is extremely slow, and EEG gamma is extremely rapid. And this takes place over around 2.8 seconds in this example. So now we collect all the best fitting co-activation frames for each of the 7 templates, the first 7 Yau templates. We then take the average of these best fitting co-activation frames and plot it on the cortical surface. we see this result. And so we now compare the average of all the best fitting coactivation frames to the original blueprint, and we see a strong correspondence. And this is true for all the templates, and it's also true across the different timescales. So this is delta, and this is theta, alpha, beta, gamma, and for all the timescales, we see this strong spatial correspondence. So we've provided a visual confirmation that the blueprints are fitting the coactivation frames quite well. But now we provide statistical evidence that this is the case. To do so, we compare the empirical in purple to two different null models in blue and red. This is the empirical result for the infraslow fMRI timescale, and this is the empirical result for the gamma EEG timescale. And so each dot is the mean correlation of all the best fitting blueprints for the run. And so we can see that the empirical result is significantly higher than the two nulls. The first null in blue represents the case when blueprints have been scrambled and therefore contain no ICNs. The second null in red represents the case when coactivation patterns have been scrambled and contain no ICNs. And this is achieved by phase randomizing the time courses. So in case one, blueprints are scrambled and contain no ICNs, and in case two, time series or coactivation patterns are scrambled and contain no ICNs. And in both cases, they are significantly lower than the empirical, indicating that, yes, there are ICNs in both the blueprints and in the coactivation patterns. And this is true for all the different timescales. So we now look at different ways of quantifying the temporal dynamics or capturing the temporal dynamics at each of the 6 timescales. So in this case, we are looking at the fractional occupancy of the 126 state blueprints. And we can already start to see strong indications of correlation between the slow timescale at fMRI and the faster timescales in EEG. Now we look at the mean dwell time in milliseconds at each of the 6 timescales for the 126 state blueprints. And I draw your attention to the different scale on the y-axis. So for infraslow fMRI, we see the mean dwell time is about 4 to 5 seconds. The mean dwell time for delta is about 150 milliseconds, then about 100 milliseconds, then about 70, then about 30, then about 20 at the fastest timescale gamma. And as for the fractional occupancy, we also see strong correlations between the slow fMRI timescale and the fast EEG timescale. So to make this more concrete, we perform the correlation systematically for all the different pairwise combinations of timescales. And we see, yes, indeed, infraslow fMRI is moderate to strong correlated with the 5 fast EEG bands. And that's true for fractional occupancy, and it's true for the mean dwell time. And these correlations are well above what you would expect if they were due to chance. So now we're looking at the transition probabilities for all 126 states. Their diagonal captures the probability of remaining in the current state. The off-diagonal elements capture the probability of transitioning to a new state. And right away, we can see that there's a strong spatial resemblance at all timescales of these probabilities. So if we correlate these transition probability matrices across all combinations of timescales, we find again that the infraslow fMRI timescale is strongly correlated with the EEG, the faster EEG timescale. This is true for the off-diagonal, and it's true for the on-diagonal to a lesser degree. So if we next quantify how many ICNs turn off or turn on at each particular time step, and represent that as a portion of the total number of time steps, we generate this pie chart for the infraslow fMRI. And we can see that this pie chart suggests that the vast majority of transitions are occurring between spatially similar blueprints when one ICN turns off or one ICN turns on. And this is true for all the different timescales. And I would point out that this transition structure is represented in the transition probability matrix in this oval pattern of high probability. So we would like to now find out how much of the probability in the transition probability matrix is assigned to the off-diagonal as compared to the on-diagonal. So if the probability is largely stacked on the off-diagonal, it means the state blueprints are transitioning rapidly. And if the majority of probability is on the on-diagonal, it means the state blueprints tend to remain in the current state, which is the case for infraslow fMRI. And so, although the probability matrices are highly similar, the proportion of probability is assigned to the off and on-diagonal elements in such a way as to generate a different switching rate for each of the 6 timescales. So infraslow transitions very slowly, and gamma EEG transitions very rapidly. So our primary results suggest that across timescales, coactivations may be described as combinations of ICNs or state blueprints. These states appear to display shared temporal dynamics. So we conclude that shared spatial and temporal information pervades the organization of the connectome at all timescales. We therefore posit spatio-temporal principles governing the dynamics of the connectome. We suggest that multiple streams of connectome dynamics that unfold concurrently and independently may serve as parallel information or communication channels. Thank you.